Okay, thank you very much. So welcome to this week's session, in which we'll be focusing on computer vision. And so we'll be talking on computer vision. And just to recap what we did previously, last week we introduced on neural networks, how you could get started with neural networks, what they are and what you could do with them, and how you could effectively train, like you could solve problems using neural networks. In this particular week, we'll look differently we will also be looking at neural networks, but a different kind of neural network, but applied to a different type of data set, which is images. And yes, so I think I will just get into it now. So just to also recap, so this is like the GitHub page for this Arewa data science deep learning class. And the primary resource is this Zero to Mastery Learn PyTorch for Deep Learning. So this particular week, we'll be looking at PyTorch computer vision. So I will just open the notebook on my Colab. Yes, so computer vision primarily deals with images. How could computers learn to perform tasks effectively on these images? So as a human, when you look at image, you don't really do much of thought in how you analyze the images. Like you look at it and directly what you want to do, like there is some kind of direct mapping for you. But when it comes to a computer, it's difficult because like it tries to learn from scratch and you need to tell it what to do and how to do it. So that's why like it's important to design systems that will help like computers see images and think well. And just to talk about like the different problems you could find in computer vision, one of which is maybe classification, which we have talked about. Imagine you look at an image and in that image, you want to identify between a dog and a cat. So easily when you look at an image, you know what particular things or features of that image or animal you look at, and you quickly identify if that animal is a dog or a cat. But for a computer, it's different. You need to train it to learn what are the features of a cat. You could either do it manually, which to go back in history, like there is what they call handcrafted features, in which you give to your computer and it learns to maybe classify some features of either animals or any feature of objects. But now using like this deep learning approach, which we'll be focused on, so your computer automatically learn these features instead of you providing those features. And computers learning these features themselves makes much more effective and has higher performance. And so please can we kindly mute our mic? In one order, if you can kindly mute our mic just so that like other participants too can hear. But if you have questions or any comments, feel free to just unmute your mic and speak. So, and one other tasks in computer vision include what you have here, like object detection. So object detection means like you look at an image and you detect like that object exists in that particular image. And in most cases might involve localization, where you locate where the object is in that image. So maybe looking at this image here, so you could see like there is a pizza and there is like someone doing some thumbs up on the image. So easily you could perform object detection here. Is there XYZ object in this particular image? Is there a pizza in this image? Is there a bow in this particular image? Is there this tiny car here in this particular image? So that's like where object detection comes into play. Then there is a particular task in computer vision, which we call segmentation. And more of segmentation is more of like when you look at an image, can you take out an object from that image? Or more precisely, can you find out the boundaries of that particular object? So when you look at an example, for instance, we could say, let me see. Yeah, so maybe we could just use this image, for instance, and you look at it. this image here. So what you could see, even though it's too small, you could see like a lady, and behind her, it's more of like some background that has like some uniform color. So that's where that's the effect of segmentation. So one good example of maybe image segmentation, you could say, if you've seen someone in a video call and his background is blurred, so you could say like image segmentation has been effectively used there. But in this case, it's more of like a video, because what happens is you could see the person completely, but the background is blurred. That means you're looking at one instance of the image, the person's maybe body has been carved out, then everything in the background has been more of like nullified or changed to any other color. So that's where you could see the application of image segmentation, and it has very vast application too in maybe the medical sciences. So it's always good. Then one good question you might ask, you have understood what's the general concept of computer vision, where is this useful, and why and where maybe can I use this particular systems that I am going to learn to build. So computer vision can be used in several areas. So just to highlight a very few examples so that we could move forward, let's look at agriculture in this case, where you have plants, and plants naturally might or might not have diseases. And considering if you are dealing with a very large scale farming system or very large farm in that particular case, it might be difficult to just look into every plant manually and maybe tell their diseases. So computer vision can come into play, in which you take the pictures of these plants, or a drone moving around taking pictures of these plants, and automatically can tell you what particular disease this plant has, and yes or no whether it has diseases or yes. So that's one application of computer vision. Another is security. In security wise, one example I would say is where you have retail stores. So in retail stores, it's difficult to keep track of everyone because people are moving in and out. So with these computer systems, you could avoid theft in numerous ways. So that's just one key like possible ways you could use computer vision, but like anything that deals with images, so you could definitely apply computer vision into those particular problems. So yes, so what we are going to touch on, it's more of like computer vision problems, how you could approach and tackle them. So still using the PyTorch workflow we talked about some weeks back and highlighted also last week. So if you maybe don't understand it, please go back to those videos, or you could just maybe send a message in the group. So I think particularly you'll be looking at this Torch Vision library, which is used for most computer vision tasks, because it has a set of tools that you could use for simplifying problems. And majorly we look at what's like a convolutional neural network. Then likely, if there is still more time, we would just go deep into convolutional neural network, because it's more of like, it's what's very key in when you try to solve one image task or another. But in very large networks, there are different ways in which like this CNN convolutional neural networks are being connected to one another. But we will highlight a few of them here. So I would just skip a few things, most of which we have. 1 minute. So also feel free to if you have any questions, send them, or any comments, just feel free to unmute your mic if you want to say anything. So these are a few libraries we'll be using, but like within the course of our discussion, I will highlight their importance here. So here is just a few importations. So major part of this code, you have them already, like from the Daniel's course. So I would just like add more pointers and give maybe more vivid explanation, just so that you could get the gist of things. Yeah. So here we're just majorly importing libraries. Here we are importing like PyVision libraries. Then yes, so I'll just go on, but feel free to stop me at any point in time. So the major So like I said, in CNNs, in computer vision, what you majorly use is images. So unlike the previous data set we used, in this particular data set, so you remember in the tabular data set you used, you had like some, maybe let's say feature 1, feature 2, feature 3. Then you had like a target in which you are trying to, your model to predict. But in this particular case, it's different. What you have is an image. So for you, as assuming you have an image of maybe a boy just standing here. So for you as a human, just looking at the picture, it kind of makes sense. You don't need to do much complex thinking to understand what the image stands for. But for a computer, it's totally different. So you need to find an approach that helps you to identify or do some kind of thinking on this particular image. So first, you need to look at how like an image is structured on a computer. So when you look at an image, it's primarily breaking down into pixels, and those pixels kind of have value. So each pixel has like some sum of value. So instead of you using features in images where you have features here, so in computer vision, you look at the whole, like a whole set of pixels here. So for you to make some kind of intelligent system that could maybe do classification or maybe a regression. So any particular task you wanted to do. So it's like a different formalism entirely. So, but you do understand you have your data and there is like a target you want your data to predict. So one key thing I would say, like here, your pixels here are the features for you when you are dealing with computer vision. So that's basically it. So for this, we'll be dealing with fashion MNIST. So in fashion MNIST, it's more of like a data set in which you have a set of clothes, and those clothings are categorized into 10 different, I would say, classes. So you have shirts, you have trousers, you have shoes, but they have like 10 different categories. So one key question I will ask you, since this problem has 10 different categories, will we say it's a binary classification problem or a multi-class classification problem? Please, can you quickly type in the chat? So there are answers coming in. Yes, correct. So the answers were Bilkisu, Muhammad, Lukman, and Umar Alamintu. Thank you so much. So multi-class classification problem, because you have more than 2 classes. If you have 2 classes, it's fine. You say it's binary classification, but here you have multiple classes, so it's multi-class classification. So you want your model to predict one out of those 10 classes. So which is nice. And I'll just move forward, but please feel free to take me back any point in time. So how would we load this data set, or how would we find this data set? So Zolando Research are the original curators of this data set. So you could just click this link and it will take you there. So, but there is a simple kind of helper here that is built by PyTorch under the Vision Library dataset, which has like some culmination of like very different data sets. So easily you could just importing this library, you could easily download and get these data sets easily. So you don't need to do some extra work doing that, which is really good. So it gets you started as soon as possible. So we have already imported the data sets, maybe module that we need. So now it's just to download our data sets and use it. So in downloading the data sets, so what you could see here we are calling the module, and here we are calling more of like a subclass of that module, which is fashion MNIST. So if there are other particular different variations, which could be, let's say, MNIST and Cypher. So you could all call it and immediately it will download your data sets for you. Then what you are doing here, you are telling it you want your data to be stored in this data directory. Should create a folder for me called data here and store every data that you get from function eminence and save it here for me. So this train true, when you set train to be true, you are telling it this should be my training data. So when you call it as false, you mean that should be your test data. So which is in this case, you are telling, like, you are trying to download the test data, yes. So so here in this download argument, so what you are telling maybe Python to do, or the module to do, is to download your data set locally. So if it's downloaded locally, so it depends. In the first instance, it checks if it exists already. So if it doesn't, then it downloads it locally for you. And one special part of this dataset module is this target transform. And yes, target transform or transform. So maybe I'll talk about this transform first. So you know you are dealing with images. So you know you are dealing with images. So let's say you have this particular image. It has like some range of values, but maybe you kind of, as a deep learning engineer, you feel there are various manipulations you could make to make the data set better. So one of which, you remember when you are solving a machine learning problem and there is possibility of having missing values, or you need to do some manipulation just to make the data set maybe look better in some way. So transform is something special too in its own way, in which you could perform some transformation operations on images. So you could easily stack maybe some transform 1, transform 2, several transformation on your images, and you get like an output resulting image after those transformations. So one examples of the transformations you could do is maybe rotation, you could do flipping of images, you could crop images. So there are various different transformation you could do. And one good thing is there are already existing methods that you could use. So here, what you could see in this particular transform here is telling it to convert it to PyTorch tensor. So if you remember the advanced assignment you did first, you imported a data from NumPy using NumPy, a data set from an online resource from NumPy, then you converted into PyTorch tensor. So with this transform, assuming most images comes at NumPy arrays in most particular case, so this to tensor converts it into PyTorch tensor for you. So yeah, same thing also for this test data. The transform is the same. So the different, okay, so looking at this target transform, so it looks at your target variable. What transformation does it need to make on your target variable? You know, in machine learning, you have features and your targets. So here in computer vision, you have your features, your images, then your target is like the labels or classes you want to predict. So do you want to make any transformation on it? Is it possible like those targets are maybe letters or alphabets and you want to convert them to numbers? So any transformation you need to make, you do it here on the target transform. So yes, so I think I'll just skip and move forward a bit. So here you could see it has downloaded my data, and when you look at where it's stored, you can see it has created like a data folder here where your data is stored. So what next can we do? We can look at the image. So remember, like what I said in the previous lectures, like everything is just a bunch of numbers on your computer. So, and your machine learning model is also like a very large, maybe array of number or set of arrays of number that are trying to manipulate other numbers to maybe to do some intelligent prediction. So here, looking at your data, you could see it's a set of numbers. So first, what we do is we printed the image, so you could see, and also printed like the labels of the image. So large parts of the images are 0, and some parts have some kind of numeric value. So, and you could see the labels. So labels are the same thing as targets. So they are what you want to predict. So the labels are more of like 0. This is more of like the initial. Okay, sorry, the label is 9 here. So 9 points to another image of the class. So we'll see how to get the classes of this particular image. Then I think I would speak briefly on this particular image. So as you could see, this image has very little color. So this image is what we call grayscale image. So let me see if I should explain. Yeah, so I think I'll just explain this here. So as you can see, this image is grayscale image. So what it's telling you, it's more of, remember like those TVs you have back then where it's black and white? So it's something similar here. It's grayscale. So before you have like multicolor TV. So the difference in, let's say, gray scale image is 1 channel. And where you have colored image, in most cases, you have 3 channel, but there are other variations, which is RGB. So what this 1 channel means is, maybe we could say you have like 1 scale of color. Yes. So what you can say in this 1 GB, you could say, let's say I have this particular scale, and it ranges from 0 to 255. And when it's 0, I would say it's black. And when it's 255, I would say it's white. So here you have like various shades of black, and here you have like various shades of white. Like it's more of like changing from black to white. So that's why you kind of see the values are 0, 0 in most cases. But here I would say maybe it's 0 to 1. So it just depends on your representation. So if you divide all the values here, divided by 255, so you get like a range from 0 to 1. So that's for grayscale image. So when you look at 3-channel image, let's see 1 minute. Yeah, so when you say 3-channel image, so one common 3-channel image, so I think there are other different encodings for colors, but mostly they use RGB because it supports like the widest range of colors. You have R channel, you have green channel, you have blue channel, and each of them have their own scale from 0 to 255. So when you combine like these 3 colors, so you could get almost any color you want. So that's for colored images. But here we had, for simplicity, we are dealing with 1-channel image, so it's easier to start with. Then later on, you start to see 3-channel image, and you would use a different approach to dealing with them to solve the problems you have. So if it's not clear, please feel free to ask any question. And yes, so here we're just trying to get the shape of the image. And yes, so here, what you could find here is the channel of the image. And this dimension here, it's the height of the image, and this is the width of the image. So what it is telling you, it has, we could say 28 pixels, and from the width, it has 28 pixels also. So it's more of like a square image, which has a bunch of values. So this representation here is what you have here, where you have like the channel first, and you first have the channel here, and you have the height and you have the width. But in some cases, it might change. So in PyTorch, this is like the common way you have it. But when you load data from like NumPy, is it? So it's a bit different. So it changes to something like this, where you have channel at the very last point. So that's maybe what you should be careful for, because you'll be doing lots of tensor operations and anything can change with time. So there is a kind of blog post of which is better in some way. But if you're dealing with a very small problem, just don't bother yourself too much about it. And yes, so here what we did in this particular place, we loaded our data where we have the training and test data. Then here we could check what's the size of our data here. So here you could see you have 60 data points for training, 60,000 for training and 10,000 for tests. And you could also access with the data sets library, you could access the names of classes. You see we have t-shirt, trouser, pullover, a number of the ankle boots. So here it's more of like visualization. We talked about how visualization is usually very important. So, but here you see the image is better, more of like black and white. So you could see like the images are a bit pixelated. When I say pixelated, like you could see it's not clear enough. So you could see them in boxes. So this is in the situation where you have very small size images, where you have 28 by 28. So when you imagine something like your computer screen, in which you have something like 1920 by maybe, is it 780? So you could see this is very small compared to that. So in your computer screen now, it's something maybe 920 times 780, but this is like really small. So that's why you kind of find it with a big like box around here. But like since this is a small problem, so small neural networks or convolutional neural networks, which we will see, would be able to solve the problem easily. So, but for very large images, some people try to downscale the images to smaller size so that it could, because when you try to use neural network, it uses a lot of compute. So you're trying to find approaches to minimize the compute you need to use to solve that problem. So I think I'll just speed up and go quite fast. But don't worry, I'll explain anything you need to know. This is more of like a visualization of the images in the classes. So for you, maybe it might be easily distinguishable between a shoe and an ankle boot, but for a computer, it's not. And one way you could know, imagine I change, this looks like a shoe, an ankle boot, but if I tell the computer this is a shirt and you train your model on that, it agrees by default it's a shirt. And anytime you want to make a prediction, it tells you it's a shirt. So you should know, like, by default, the computer is not intelligent enough. You need to feed in the right amount of the right or correct data for it to learn to predict effectively. So, and yes. So one thing before we try to go forward, we have our data sets. Now, what we need to focus on is the data loader. So what the data loader does, it's more of how we should load our data from any storage we have. So what amount of data to return and how those data should be like arranged in space. So let me just see. So yes, so usually when you try to do deep learning, so most of the time you try to train on like batch data. So what batch data means, instead of fitting everything into your model, like all the data sets, like let's say in this case, you have 60,000 of them, fitting them all at once. So you start training it by small size data, which is it could be between the range of, not much of range. It could be a size of 32, 16, 64, maybe 128. So you try to fit small size data. In this particular case, you train the model in an inexpensive way so that it could maybe train not faster, but better. So you get like easy results than fitting in like 60,000 images at once. So you might not have enough memory to like pass that into your model at once. So you visually try to batch your data. So a good place where you could set your batch size, it's in the data loader itself. So what you could do, from the utils, you get this, import your data loader, and you set your batch size. You could set it to be anything, 32. So 32 is a good number, and in most cases, it works good for other people. And I think there is a popular researcher, that's Jan LeCun, who said 32 is a very good number to start. But I think one good thing, even though someone tells you it's good, but you shouldn't hold it as what you only need to do. You should also try out other values to see how it works. So what happens here, you pass in your data sets you have, and the batch size. So it's, I think I'll also talk more about it in 1 minute. So here you have your batch size, which is how should I subdivide my data? So imagine you have a data set that is, a data set that is, let me see, you have maybe, let's say these ones here are represented as images. And for instance, if I say my batch size is equal to 5, so what happens is after 5 images, I kind of truncate it. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So that way, continuously. So after each 5 images, if my batch size is 5, so what my model says is 5 images at a particular time. So that's how like batch size operates with your data loader. What happens, you could also set your shuffle here to be true. So what happens if your shuffle here is true? You know, we say when training your machine learning or deep learning model, you have epoch. So epoch is, in every epoch, like you send in all your data sets. So with this shuffle through, you are telling it like, anytime I send in my data set, should I shuffle the data or should I leave it the way it is? But there are considerable advantages shuffling your data, because it's possible your model can maybe memorize the way you pass in your data, or easily it's more effective when your data sees random samples at different particular time. So it learns better one way or the other. So I think I will just speed into things because of time. So everything follows like what you've seen before when doing maybe training any deep learning neural network. So for the very first start, you want to train a network. So I'll just explain this in the next 10 minutes. So assuming here you have an image, that we discussed having pixels. So one way to go about training this image here is to pass it to a fully connected neural network, which has something of this kind of architecture here that is perhaps connected to each other in one particular way, and with some set of output neurons, which makes some prediction. So one question, okay, let me see. So here we have like a set of pixels. Let's see, 1, 2, 3, 4, 5, maybe up to 28. And yes, so we have up to some X values here. So one thing you could do here, which is not the advisable way, but maybe the approach, like trying to show you why, you know, if you remember in the previous lecture, we talked about neural networks, which you dealt with just tabular data, passing into a neural network, making predictions. So maybe before that, one quick question. So here, we know like in our data set, we have 10 classes. So here in designing the neural network, what's the size of my output layer? What do you think it should be? You could quickly just type in the chat. What's the size? How many neurons should I have in my output layer here? So there is some answers coming in. Remember, in our data set, we have a set of images and we have like 10 classes. And here we want to train a neural network to predict one of those 10 classes. So what's the size of the output layer? So 10 is the very much correct answer. So when designing your neural network, the output layer here should coincide with like the output you want to predict, which is 10, which is good. So for the input layer, it depends. Mostly it's your input. So you just pass in your input. So one way to train images, it's more of like you flatten everything. So instead of having this kind of grid here, so everything becomes maybe one long column of input where you have maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe lots of pixels. So, and you pass these pixels here to your neural network. So that's one approach you would go. But that's even the initial approach most people have been doing before, maybe past 20, past, yes, maybe past 20 years. That's in the 1980s, where people found convolution neural network should be good. But this is just an example, just to see the performance of this linear architecture before you look at convolution neural network. So I'll just explain in the code, like what everything is doing. And we would look, I think we just jump next into convolution neural network, and you try it yourself to see how it works. So here, what you could see, we are creating a new model here, which is fashion MNIST, and we are subclassing from this NN model, which we said is like a laboratory that is designed already by the PyTorch team for you to easily get started. And here, what you are saying is you have this stack of layers that you wanted to do some classification for you for on images. So one of the first point of this, you remember what we have in sequential? Sequential, you are telling it there are sequential, it's more of, you're telling like there's a sequence of things you are expecting. So you want everything to be in sequence, where you have something of like block 1 goes into block 2, goes into block 3. So you have that kind of sequence. That's NN dot sequential. So, but when you try to do complex problems, this NN dot sequential might not be good for you. So where you have maybe something branching out, let's say this is block 4. So yes. So, but in this case, that's what NN dot sequential does, where you have sequential operations happening one after the other. So what's the first sequential operation? Here you flatten. So flatten is exactly what I explained here, where you have it's exactly this operation, where you have like a grid of images to just like one data set, one column data set with values of your pixels. Then remember what we said about linear layers. In this first layer, you have this layer is accepting this input here. So this we could see is like your input layer, which comes here. It accepts the input of these pixels that you flatten. And this is the next, it transforms from this input layer to the output layer, which we said should have 10 neurons. So here you are dynamically creating the model in which it accepts a size in which you could define, which is good because it's always good to be free of some constraints of constants. So you could be dynamic in some way. So that's basically it. And you have forward. Forward is more of like how your data is being passed from one layer to another. So it's just the flow of data. Then with this, you could train. So I think that's basically it. What this snippet of code is doing. So you have an image, you flatten, you have like a data set with one column. And from that column, what you learn from the neural network, you pass into neural network. But this is not the best way to do it. The better way to do it is using convolution neural network. I think I will briefly jump into that. So, and explain that. So I'll just run this. But please, if you have any questions, just feel free to ask. Then everything remains the same. You set your loss function, you set your optimizer, and you maybe any evaluation matrix. So one quick question, this is a classification problem. What kind of loss function should we use? Should we use mean squared error? Should we use is it cross entropy loss function? Which loss function? You could just quickly type. Let's see if you remember the discussions we had. Okay, nice. So yeah, I think I would just skip some parts and Yes, so there is some comments of cross entropy loss, which is good because cross entropy loss function is used for classification. And in this case, we are not using binary cross entropy. Thank you, Fatima. And because this problem is not a binary problem, you are doing multi-class classification. So I think one key point I will just touch upon, I'll skip this and just, so yes. So here, we'll be dealing with convolution neural network, which is one of the key ingredients in building a really effective image, a really effective intelligent system for computer vision. So why is this important? So easily you could see to find patterns in visual images. So I will give you a quick illustration of maybe why you would find it important. Imagine you have an image of, okay, let me see. Yes. Let's say you have this maybe 4:3 image. Maybe you have also this something similar here. Yes. So the challenge here when you try, so assuming these are images of numbers, and assuming we have a simple number here that is 2, but you could see like this 2, this is 2, but in image A and B, they are positioned differently. So when you try to use the previous method, let's say we try to make everything we try to flatten everything. So I would just quickly assume like when you flatten everything, so maybe we'll have maybe 12 grids. So I would just say, here you could see like the initial part of the 2. You could just mark 1, 2, 3, 4, 5, 6. Yeah. So here you could see, yeah, maybe 7, 8, 9, 10. You could see like easily the location of maybe pixels of the 2 here lie between the first pixel here, something like this, and goes a bit below. Maybe you could just assume it to be this. But in the second image here, it's more different. So it's a bit below. So maybe something roughly like this. So you could see like there are a bit of differences when you try to just use the flattening operation. But the key idea behind convolutions, it tries to avoid this, like they call them translation. So an image, when you say something has translated, it has moved like from one distance to another. So by introducing what they call like convolutions. So convolutions, it's 1 minute, let me just clean this. So what you have in convolutions, you just have a small, what you call filter. So which is maybe more of like a mini image, but it has some kind of numbers. Let's say 1, X, Y, Z. It could be any number. So AB. So what happens is these convolutions kind of travels on your images and performs some operations, but it traveling in an image like kind of makes it better for you to, so it avoids this kind of problem, because in this case, this convolution travels within this image and maybe might cover all this particular part. As you could see, it has covered your 2 here, and it continues traveling like grid after grid, yes, all around the image. So in another case, it would travel to this image 2 here, and it will pick up this 2. So that's maybe the key, maybe the little intuition of how convolution neural networks are better. So they try to detect more hidden patterns compared to you just flattening your layers and just training with your neural network. So convolutions are very key. And yes, just to highlight, like before neural networks, they did use convolutions, but they use handcrafted convolutions that are manually fixed. So what you have this, either you could say convolution layer or kernels. So you have kernels for every operation. When you want to detect the edges, you have a kernel for detecting the edges. When you want to do what's the name? Yeah, when you want to do the edges, yeah, edges and other operations. So you have several kernels for doing them. So, but with neural network, your neural network learns the numbers in this kernel here that would help it to solve the task more effectively. So yes. So yes. So feel free to ask if there's any question you want some explanation on. And maybe tomorrow better we'll look at maybe some little maths behind like the convolutions, and maybe I could maybe explain it better there. So what happens is when you have, let's say, an image here. So let's say an image of a person here, and your convolution acts on it. Let's say you have this convolution kernel here with some values here. So your image, let's say your kernel goes into the images, then you have a resulting output here. So your resulting output is also, it has like a form of an image, but it has like some new values here. So these new values, we call it like activation maps. So what happens is when there is a better way for a computer to learn. So it learns that like using this particular and some numbers. So when it learns, it learns to generate these numbers, which best helps it to make some predictions. So what you would notice is in the first few layers, your convolutional neural network learns some very low-level features. So when you look at a human face in some particular instance, so you could see maybe the eyelash, the nose, the mouth, and everything. So those are maybe high-level features. But when dealing with neural network, let's say you have some cascade of layers. The first layer, what they detect is like the edges. And yes, so the subsequent layer try to develop high-level features. So in the later layers, you could see maybe it has learned to detect the eye in some particular way. So it does like the best it could do to learn effectively. So I think we still have like 7 minutes. So I will just talk about the code for the convolution, but hopefully tomorrow we'll look at convolution in depth. So there is this CNN Explainer, which is a good website to see some visualization of how convolution work. So yes. So there are two things that go together with convolutional neural network. One is the convolution itself. Then the next one is pooling. So what happens when you do convolutions is let's say you have like an image, and that image is passed, or it kind of is passed into an image. So what happens, in most cases when you pass this into it, you most likely would get like some values, and you want to reduce the size of these values. So that's where like pooling comes into play. When you use a pooling operation, so a pooling operation is just to reduce the size of the output of the feature of the convolution operation here. Let me see. Yes. So a pooling operation happens somewhere here. So, and before you get your activation map, yeah. But I think don't worry much about it. Maybe tomorrow we'll explain better. So because it requires like some time to explain. So, but also I'll also giving like more resources if there are more better resources to learn out there. So here we'll explain a bit of what the code is doing. And I think after that, we might call it a day. So here, when you look at it, it's the same structure as we have in previous, maybe PyTorch code. You you are creating the model here called version MNIST model V2. Then here you are initializing some maybe some tools in which you would use for training your network. So first you have this this block. So maybe this block has, let me see, this block has a set of operations you want to do. So you could easily look at it like a combination of several layers of neural network. But here, most of the neural network is convolution neural network. So convolution neural network here, it's 2D, just trying to tell you it's in form of in 2-dimension shape. So just like an image. So when you look at this block in the very first instance, what you could see, so this block accepts an input of channels and an output of channel, and it has like some kernel size of 3. So when you remember when we dealt with neural networks, you tell it what's the input coming to it, what's the output should it return to. So it's similar in the case of convolution neural networks. So what's the output of the preceding layer? So that's where you have the input here, and what's the output you're expecting from that layer of convolutions. So this kernel size, we call it to be 3. So in this case, you will say your kernel size is 1. But if you want several kernels, so you stack them together, maybe you could say you have another additional kernel here, which is 3. So most times, the more the kernels, the more better your predictions. But you should also know it comes with the downside. So when you have more kernels, you are going to be doing more operations. So it might take time to train. So this is like what's kernel size. Then stride, we have what we call stride. So let me 1 minute. So when you have stride is how your kernel moves along your images. So assuming you have an image, let's say this is a very simple image. Okay, let me just do it this way. That has some kind of values here. So when you say stride, what you mean in the very first case, let's say your convolution, you have a 2x2 convolution. When you say stride is in the very first instance, it should move like when you say a stride of 1, it should move between the pixels by just after 1 pixel, it should move along each other. Let's say this is your your first iteration. In your second iteration, you want the kernel to be here. I is equal to 1. Then in the maybe third iteration, you want the kernel to have moved along here. Maybe that's I is equal to 2. That's a stride of 1. But you could also increase the stride size either vertically or horizontally. So here, when you say it's a stride of 1, you see like both vertically, it's equal to 1, and the stride horizontally is equal to 1. And let's say we increase the stride number. So you could still the same using, let's say the stride here is 2. So in the very first instant, you could see your convolution covering this point. Let's say this is the first iteration. So in the second iteration, instead of it moving just 1 block, it will move like 2 blocks. So it will move to this particular point. And yes, you have your kernel here, and that's where you perform your convolution operation. So tomorrow we will look clearly into convolution operation, and you look at it. So it's always good to have some visualization of what happens underneath, just so that you understand the mechanism, and easily you learn what's the best way to adjust your parameters so that your model could learn effectively. So that's for stride. Then finally, it's padding. So padding here means when you have an image, let's say you have an image of this size. And and you have, what's the name? And you have a kernel of this size. So when the kernel first goes into this image, so the problem is it doesn't fixate on this first pixel. So in most cases, it's good to add padding on your image. So padding can be in form of zeros. So you could just add on your image, you could add some values, some additional values to your image, just so that your kernel can go everywhere on your image. So you could put zeros everywhere here, and that's where you have everything padded. And so now your convolutions can easily sit on your image, centered by the first pixel. So yes, so that's where padding is important. So yeah. So everything kind of follows like the concept we've talked about. So with sequential, you have everything layered in order. So here you could see in the very first layer, you have convolution layer followed by an activation function, then a consequent convolution with an activation function, then finally a pooling. In most times, this arrangement, there are various theories of how you could arrange like one layer and the other. Some do say you should put the pooling layer before the activation layer. So it depends. You will need to try things out to see what works best for you. And yeah. So so this is like the first block. Then you would see something similar in the second block with a few variations. So at the end of the second block, what you often find after everything, you find at the end of something like this, what you often find, you still have something 2D in shape, but you need to convert this 2D into some kind of predictions of 10 values. So here, what happens next is you flatten the 2D you have from this block 2. So you could see what happens. Your data comes here first, which is a set of convolutions. Here, you have something 2D in shape. Then next, it goes here, this block 2, you have still something 2D in shape. I'm not sure of the size now, I'm just visualizing. Then finally, this classifier, you could see what happens next. It flattens this 2D shape you have. So you have something 2D in shape. It flattens it into something of 1 dimension. And you have a resulting linear layer in which this goes to and output some values. Yes. Yes, so your output here, it has to be what you're expecting for your predictions. So yeah. But here, what you would notice here, these outputs here are raw numbers, which remember when we talk about your output should be probability distributions. So here at some point, maybe later on in this particular course, there would be a softmax here so that you could have probability distribution, because it's easy to know which is the more what's the prediction with probability distributions. So I think I have maybe said enough here. So I think I would just so please, if you have any questions, please do ask. So I think I've spent more time discussing, but tomorrow we'll talk more about ideas of convolutions, and you could see them clearly, and maybe any calculations that follows within them. Yeah, please, if you have any questions, you could ask. And yes.
Assalamu alaikum warahmatullah.
Wa alaikum salam.
Yeah, good evening, sir, and thank you for this intuitive session.
Yeah, thank
My
you.
question is regarding the network architectures.
Yes.
I wanted to ask whether the PyTorch has something similar to TensorFlow functional API architecture. Does it have, and like, if it have it, like, how is it going about?
Okay. Honestly, it's been long I use TensorFlow, but when you say functional API architecture, okay. Is it like the one where everything is pre-built for you already?
Yeah, like it's a kind of architecture in which is like far more flexible.
Yeah.
Like the output can even be more than two or three. Like that, like the input can be many. Likewise, the output can be many.
Okay,
Yeah,
okay. Yes,
yeah,
I
yeah,
think in some way, like Python supports everything, but the only issue with, or the only, it's not actually an issue, it's a good thing because like with PyTorch, it gives you like very massive flexibility, but I think it comes at a cost because you have to define everything yourself. Because in PyTorch, like this entire training loop in which you have here, you just say something like model.train and it trains for you easily. You don't need to go through the trouble of defining like your training loop. So I can't say maybe it has functional. I honestly don't know, but I think maybe any functionality you are looking for, I think you will definitely see it in some way in PyTorch, but most things you have to define them in PyTorch. Yeah. I think there is Fatima, please. I think your hand is up.
Assalamualaikum.
Wa alaikum salam.
Good evening, sir.
Good evening.
My question here is I see in this PyTorch we also have a way of padding in the
Yes.
CNN. Is it similar to the way that we can truncate our padding like in TensorFlow, or we can specify the position of the padding, be post or pre
Yes.
pre padding or post padding?
Sorry, please, can you come again with the last statement, please?
I said, is it a similar way that in PyTorch we can do, like, let's say, post padding, that is the zeros to come after a given set of vectors, or pre-padding, or to specify the location of the addition we wanted to add in the sequence of the
Okay.
neural convolutional neural network.
Okay. Yes, I think there are various forms like where your padding would can go 1 minute. Let me see. So here, let me see, 1 minute. Yes. So here for the padding, you are so here the padding can come in various ways. You can set the padding to come like so you could have, let's say you have an image, you could tell it what values you could have for the padding. First, you could set with PyTorch, you could set like the values. You could set the padding to be anything like 2, 3. There are different methods you could use. So you provide the method you want here. You could also use mirroring, in which you mirror the last pixels and maybe take them just below the padding. You could also set, I think that's the padding height or anything. So you could set like how many layers of padding you want for your pixels. So I think that's what you could get. And there are various other features you could have within your, what's the name? Within your convolutions, yes. I don't know if that answers the question, but happy to maybe talk more on it.
Yes, sir. Thank you.
Yeah, no. So any questions, maybe in the next 1 minute, if there is any questions, just feel free. You could always ask anything. So maybe, okay. So I think finally, I don't think there are any questions. So just to recap, hopefully I will try as much as possible to get feedback on the assignment week 2 tomorrow. And also I would make, if you have submitted towards the end of the day, I will pair you with your colleague that will grade you and also give like a template for grading so that it won't be anything strict and okay, just so that at least it's easy to see other people's code and you could maybe comment, and when you see other people's code, you could learn from it additionally. And also, I think it also helps me one way or the other. So I think there is a question on vision transformers and CNN, which is good. CNN better. So there is, yes, I can't I can't say 100%. So one recent tweet or experiment I've seen is there is not much significant change of vision transformers with CNNs. So even though they work well in some particular tasks, but like when you average out everything, like vision transformers are not completely as maybe like they are not like overpowering CNNs, but it's also like a new improvement. And one thing maybe I would say, even though I don't have much significant experience, like vision transformers would be significantly useful when you try to deal with multimodal systems. So that's where vision transformer will be a huge plus. Because CNNs itself, like you just use them on images, which is good. But when you try to do like multimodality of videos, so, and when you need to deal with the audio component of things, so it becomes something complicated and you need to deal with, maybe you bring in other models to utilize or to learn from your audio. But I can't say 100%, but based on like the tweets I've seen, so like you can't see vision transformers are better 100, like there is like trade-offs. One is better than the other in some way, yes. But I can't say 100%, yeah. So yes, thanks so much for the questions. So I think, yes, so I think, so I think I will see you tomorrow, inshallah. I think tomorrow primarily would be discussing, I would introduce on the convolutional neural networks. That's more in-depth with the calculations, just so that you could see them. But you don't need to like know the maths. You could just, as far as you understand the intuition of how things work, you could get on with it. And hopefully I look forward to answering maybe more of your questions tomorrow. And yes, so it was nice meeting you this weekend. Have a wonderful weekend ahead, inshallah.